Hello, and welcome to the Academy of Useless Ideas. Did you know that the Jet Propulsion Laboratory at NASA only uses the first 16 digits of pi for their calculations? That's right, they don't need to know the 17th digit, because who cares about that one, am I right? But seriously, the digits of pi go on forever and ever, so at some point you have to make a decision about how many digits to include in your calculations. The more digits you use, the more precise your calculation will be, but also the more time it will take. But let's get back to the real world, where we have actual calculations to make. Did you know that Voyager 1 is about 15 billion miles away from Earth? If you were to calculate the circumference of a circle with the diameter, you would only make an error of less than half an inch using just 16 digits of pi. That's pretty precise, but what if you wanted to be even more accurate? Well, if you wanted to calculate the circumference of a circle with a diameter equal to the observed size of the universe, which is 46 billion light years, in case you were wondering, and you wanted your error to be smaller than the diameter of a hydrogen atom, you would only need to use 38 digits of pi. Let's talk about pi for a moment. Sure, it's irrational and its decimal representation goes on forever without repeating, but it's not the only number with that property. In fact, any irrational number requires infinitely many digits to describe accurately. But in practice, we only need a finite number of approximations to get by. That's where sequences in metric spaces come in. By modeling these approximations, we can see how a sequence gets closer and closer to a point, which is key in understanding convergence. A sequence over a metric space X is simply a function S from the natural numbers to X, where Sn denotes the nth element of the sequence, and Sn in parentheses denotes the entire sequence. Let's take a look at a concrete example, the real-valued sequence 1 over n. As a function of the natural numbers to the real numbers, we can represent it as a graph with the natural numbers on the x-axis and the sequence values on the y-axis. In this case, the graph looks like a series of points that get closer and closer to zero as n grows larger. This visualization technique can get messier when working with sequences in higher dimensional metric spaces, like in the plane. In these cases, it's easier to just plot the sequence values Sn and label them with their corresponding n values. Think of it like mapping out a treasure hunt. The sequence values are the clues, and the labels tells you which steps of the hunt you are on. Now, some sequences have what we call convergence, meaning they approach a specific point as the sequence progresses. For example, take the real-valued sequence 1 over n. As n gets larger and larger, each element in the sequence gets closer and closer to zero, but never actually reaches it. It's like a never-ending party of infinitely many people who are always getting closer to their destination, but never quite getting there. On the other hand, some sequences do not converge at all. For instance, the real-valued sequence -1 to the power of n oscillates between positive and -1, like indecisive partygoers who can't seem to make up their minds. To make sense of convergence, we need to give it a rigorous mathematical definition. To understand convergence, we need to use the open balls of the metric space like a magnifying glass. Let's take a closer look at the sequence 1 over n using this perspective. We can see that the entire sequence lies within the open ball around 0 with a radius of 1. If we use a more powerful magnifying glass, such as the open ball around 0 with a radius of 0.1, we notice that all but finitely many elements of the sequence lie inside it. As we zoom in further, more and more people are left out, but importantly, only finitely many are left out. This is true for open balls around 0, but for any other point you can find a magnifying glass that leaves infinitely many people out. It's like the party is only happening at one location, and any other location leaves infinitely many people behind. On the other hand, let's take a look at the sequence -1 to the power of n. In this case, there are only two candidates for being the location of the party, -1 and 1. However, no matter how small the magnifying glass is, we can never fit all but finitely many elements of the sequence inside a single open ball around either of those points. This is because the sequence keeps bouncing back and forth between -1 and 1. It's like having two parties happening at the same time, and people keep switching between them. As a result, this sequence does not converge to any point in the metric space. With these examples in mind, we are able to give our definition of convergence. A sequence xn over a metric space X with distance d converges if there exists an x star in X such that for every ball around x star, there exists a natural number capital N such that for every little n smaller or equal than capital N, xn belongs to the ball B. Think of x star as the location of the party, the ball B as a particular magnifying glass, and the natural number n as the starting point of people who are making it to the party. When a sequence converges, we call x star the limit as n goes to infinity of the sequence xn, and we will denote it by lim of xn. Note that every ball around x star is characterized by its radius, so equivalently, a sequence xn converges if there exists an x star in X such that for every epsilon greater than 0, there exists a natural number capital N such that for every little n greater than or equal to capital N, the distance between xn and x star is smaller than epsilon. This definition may seem a little bit daunting, but as long as you remember the intuition behind it, it will be easy to recall. From the definition we can check that if a limit exists, it must be unique. Indeed, if there were two limits, you could put disjoint balls around them, and therefore only one of those balls could contain all but finitely many elements in the sequence. Also, with this definition, we can prove the convergence of sequences. For example, the sequence 1 over n converges to 0 because given any epsilon greater than 0, by the Archimedean property, we can find a natural number capital N such that 1 over capital N is smaller than epsilon. Therefore, for every little n greater than or equal to capital N, the distance between 1 over little n and 0 is smaller than 1 over capital N, which is smaller than epsilon. One advantage of using abstract definitions is that they allow us to think more systematically. For example, from the definition, we can conclude that a sequence does not converge if for every x star in X there exists an epsilon greater than 0 such that for every natural number capital N there exists a little n greater than or equal to capital N such that the distance between xn and x star is greater than or equal to epsilon. Using this, we can show that the sequence -1 to the power of n doesn't converge. Specifically, for any arbitrary real number x star, we can see that for every natural number capital N, either n or n plus 1 lies outside the ball of radius 1 around s star. Therefore, -1 to the power of n cannot converge to x star.